Hello, welcome back, wherever you are tonight. And I wonder about that. Genuinely, at this hour, what particular room, what particular light, what particular shape of quiet has gathered around you right now? I'm glad you're here. This is a good hour to have found your way to. Whatever the day held, it's behind you now, and this is what comes next. Go ahead and settle in properly. Not the tentative kind of settling, still half alert for something else. The full, complete kind. Let your weight sink entirely into whatever is holding you up. Let your shoulders finally release whatever they've been carrying. Let your breathing slow into a rhythm that doesn't need to be managed, just allowed. You don't need to remember anything specific tonight. What stays with you will stay, because it found something in you already waiting for it. The rest will simply pass through, gently, and that's exactly as it should be. This isn't a lesson to be studied. It's a long, slow unfolding of something true, offered at whatever pace lets your eyes close on their own. If you're new here, welcome. This is Late Space, and what we do is take the largest ideas we can find and slow them down until they fit the shape of a quiet evening. If this feels like somewhere you'd like to return to, a gentle like or subscribe helps other people find their way here too, on their own restless nights. But that's for later, when you're more awake. Right now, there's only this. Tonight, we're going to do something a little different from our usual evenings together. We're not going to follow a single spacecraft, or a single discovery, or a single strange and beautiful object. Tonight, we're going to try something both simpler and, in its own way, considerably larger. We're going to try to measure the actual size of everything, not metaphorically, not as a poetic gesture toward the idea of vastness. Actually, carefully, step by step, starting from exactly where you are right now. This room, this bed, this particular arrangement of walls and ceiling, and moving outward, patiently, in expanding circles, until we reach the very edge of what it is possible for any instrument, any telescope, any measurement humanity has ever made to actually detect. This is going to be a journey of scale, and I want to warn you gently, before we begin, that scale is a strange and slippery thing for the human mind to hold. Our brains, remarkable as they are, evolved to navigate distances measured in footsteps, in the reach of an arm, in the distance across a valley or a village. They were never built to intuitively grasp a distance like 93 billion light years. No brain has ever been built for that. Not mine, not yours, not anyone's. But we can approach it anyway. Slowly. Patiently. Building each step from the one before it. The way you'd climb a very long staircase in the dark. Not by trying to see the whole staircase at once, but by trusting that each individual step is manageable, and that enough manageable steps, taken one after another, eventually carry you somewhere extraordinary. Let's begin exactly where you are. Close your eyes when you want to. We have all night. Right now, tonight, you are lying somewhere on the surface of a sphere. That sphere is called Earth, and it has a diameter of about 12,742 kilometers, roughly 7,918 miles if you measure straight through the center from one side to the other. This number, on its own, is already almost too large to properly feel. If you tried to drive across that distance at a steady highway speed without stopping, it would take you more than 5 days of continuous driving. And that's simply the diameter, a straight line through the planet's core, not the curved distance across its actual surface, which is considerably longer still. And yet, in the context of everything we're about to discuss tonight, Earth's 12,000 kilometers is, quite genuinely, one of the smallest measurements we're going to encounter. It's our starting point precisely because it's still, barely, within the range of something a human mind can hold. A distance you could, in principle, actually travel, actually experience, actually watch pass beneath you through the window of a very fast airplane. Let's step outward from here, gently, to the next rung of this ladder. The moon, our planet's quiet companion, sits at an average distance of about 384,400 kilometers from Earth, roughly 30 times Earth's own diameter. Light, moving at its impossible, unchanging speed of just over 186,000 miles per second, takes about 1.25 seconds to cross that gap. When you look up at a full moon, you are seeing it not as it is in this exact instant, but as it was a little over a second ago. A tiny, almost imperceptible delay, the first hint of something we're going to encounter in ever more extreme forms throughout the rest of tonight's journey. The simple fact that to look outward into space is always, in some sense, to look backward into time. The Apollo astronauts who travelled to the moon took roughly 3 days to make that journey, travelling at speeds far exceeding anything in ordinary daily experience, and even then, 3 days felt, to those who lived through it, like a genuinely long voyage. The longest most human beings had ever undertaken. Let's step outward again. The Sun, the star at the centre of our entire solar system, sits at an average distance of about 150 million kilometres from Earth. This particular distance is so fundamental to how astronomers measure the universe that it has its own name, the astronomical unit, or AU. 1 AU is, by definition, the average Earth-Sun distance, and it becomes, almost immediately, one of the essential units we'll need as our journey continues to expand. Light from the Sun takes about 8 minutes and 20 seconds to reach Earth. This means that every single time you have ever seen sunlight, every sunrise, every warm afternoon, every quiet golden hour before dusk, you have been looking, in a small but genuine way, into the past. Not a dramatic past, not a past that matters to anything you're doing, but a real one nonetheless. If the Sun somehow simply vanished this very instant, you and everyone else on the daylight side of Earth would continue experiencing its light and warmth, uninterrupted, for a further 8 minutes before the darkness finally, silently arrived. Already, in these first few steps outward, from your bedroom to the moon to the Sun, something important is beginning to reveal itself. Distance and time, in the universe we actually inhabit, are not separate things. They are, in a very real sense, the same thing, viewed from different angles. The farther you look, the further back in time you are actually seeing. We're going to carry that idea with us for the rest of the night, because it becomes, as our journey continues, not just an interesting detail, but the entire key to understanding how anyone was ever able to measure the size of everything at all. Wherever you are, I hope you're comfortable. Let's pause here, briefly, and let these first few steps settle, before the numbers begin growing considerably larger and considerably stranger. Let's continue outward now, past the Sun, toward the outer edges of our own solar system. Jupiter, the largest planet orbiting our star, sits at an average distance of about 5.2 astronomical units from the Sun, meaning sunlight, having already travelled 8 minutes to reach Earth, takes a further 35 minutes or so to continue onward and reach Jupiter's cloud tops. Saturn, with its magnificent rings, sits further still, at about 9.5 astronomical units, its own light delay stretching to roughly 80 minutes. And then, at the very outer edge of what we traditionally consider our solar system's planetary architecture, Neptune orbits at about 30 astronomical units from the Sun, a distance so vast that sunlight, even moving at its impossible, unchanging speed, requires just over 4 hours to complete the journey. When the Voyager 2 spacecraft flew past Neptune in 1989, an encounter we've discussed in earlier conversations here at Late Space, the radio signals confirming that historic flyby took those same 4 hours simply to travel back to Earth, meaning that by the time mission controllers on the ground actually received confirmation that the spacecraft had survived its closest approach, the spacecraft itself was already, in real time, 4 hours further along its outward journey. Beyond Neptune lies the Kuiper Belt, that vast, sparse ring of icy bodies we explored together in an earlier episode, extending outward to perhaps 50 astronomical units from the Sun. And beyond even that, astronomers believe, lies the Oort cloud, an enormous, only theoretically confirmed spherical shell of comets and icy debris, potentially extending outward as far as 100,000 astronomical units, a distance so large that it begins to blur into an entirely different category of measurement altogether. This is, I think, worth pausing on. 100,000 astronomical units. That's 100,000 times the distance from Earth to the Sun. And even this staggering figure, this outer boundary of our own solar system's gravitational influence, represents only the very first, smallest step of tonight's actual journey. We have not yet left home. Not really. Everything we've discussed so far, the Moon, the Sun, Jupiter, Neptune, even the distant, sparse edges of the Oort cloud, all of it belongs to a single star system, our star system. One among hundreds of billions in a single galaxy, which is itself one among trillions of galaxies scattered across everything else we're about to explore tonight. This is the point in our journey where the astronomical unit, useful as it has been so far, begins to become impractical. The numbers required simply grow too large, too unwieldy, to remain useful. And so astronomers, needing a new and larger unit of measurement, turn to something we've mentioned already tonight, almost in passing, the light year. Let's define this properly, carefully, because it's going to be the primary unit of measurement for the rest of our journey tonight, and I want you to feel its actual scale before we start using it to measure genuinely enormous things. A light year is not, despite what the name might suggest to an unfamiliar ear, a measurement of time. It is a measurement of distance, specifically the distance that light, moving through the vacuum of space at its fixed, unchanging speed of approximately 186,282 miles per second, travels over the course of one full Earth year. Let's build this number properly, patiently, the way we build all our numbers here at Late Space. In 1 second, light travels roughly 186,000 miles, far enough to circle the entire Earth about 7.5 times. In 1 minute, it covers about 11 million miles. In 1 hour, about 670 million miles. Already more than 4 times the entire distance from Earth to the Sun. In 1 full day, light travels roughly 16 billion miles. And in 1 full year, patiently, relentlessly, without ever slowing or pausing, light covers a distance of approximately 5.88 trillion miles. Or, expressed in the metric measurements astronomers more commonly use, about 9.46 trillion kilometers. 1 light year, 9.46 trillion kilometers. This is already, on its own, a distance that exceeds almost anything we discussed in the first part of tonight's journey. The entire outer edge of our solar system's Oort cloud, that vast, sparse shell extending 100,000 astronomical units outward. Even that entire span amounts to only about 1.6 light years. Our whole solar system, planets, comets, and all, fits comfortably within less than 2 light years of space, and the nearest star system beyond our own, Alpha Centauri, which we explored together in a recent conversation, sits at a distance of 4.2 light years. Already, having taken just this one additional step outward from the edge of our own solar system to our very nearest stellar neighbour, we have crossed a gap that our fastest current spacecraft, Voyager 1, would require some 75,000 years to traverse. Wherever you are, I hope you're still comfortable. Let's breathe here for a moment, because the numbers are about to start growing considerably faster than our intuitions are built to follow, and it helps, always, to arrive at each new step feeling grounded rather than rushed. Let's continue outward now into the wider structure of our own galaxy, the Milky Way. Our galaxy is a vast, flattened spiral, containing somewhere between 200 billion and 400 billion stars, arranged in graceful, curving arms that wheel slowly around a dense central bulge. Our own sun sits within one of these arms, a comparatively minor, unremarkable spur sometimes called the Orion Arm or the local spur. roughly 26,000 light-years from the galaxy's actual center. 26,000 light-years. Let's sit with that number properly, because it represents an almost unimaginable expansion from everything we've discussed so far tonight. If Alpha Centauri, at 4.2 light-years, already required Voyager 75,000 years to reach, then the distance from our Sun to the center of our own galaxy is more than 6,000 times that distance. It is a gap so large that even light itself, moving at its impossible, unchanging speed, requires 26,000 years simply to complete the one-way journey. The entire diameter of the Milky Way, measured from one outer edge of its spiral disk straight across through the galactic center to the opposite edge, spans approximately 100,000 light-years. Some more recent, more careful measurements suggest the galaxy's faint outer disk may extend even further, closer to 150 or even 200,000 light-years, though the galaxy's edges, unlike the sharp boundary of a planet, fade gradually rather than stopping cleanly, making the exact figure somewhat dependent on how faint a signal you're willing to count. 100,000 light-years, at minimum, simply to cross our own galaxy. And within that single galaxy sit hundreds of billions of stars, an uncountable number of planets, and, as far as we currently know, at least one small, blue, water-covered world where a species capable of building telescopes and asking questions like the one we're asking tonight happened against considerable odds to emerge. Let's step outward once more, beyond the boundaries of our own galaxy entirely, into the wider structure that contains it. Our galaxy is not alone. It belongs to a small cluster of gravitationally bound galaxies that astronomers call the Local Group. A modest collection of roughly 80 known galaxies, dominated by two large spirals, our own Milky Way and its slightly larger neighbor, the Andromeda Galaxy, along with a considerable number of smaller, fainter companion galaxies scattered around them. Andromeda, the nearest large galaxy to our own, sits at a distance of approximately 2.5 million light-years. We discussed, in an earlier conversation here at Late Space, how this galaxy is slowly, steadily approaching us, drawn by mutual gravity, and how in roughly 4 to 7 billion years, our two galaxies will begin the long, patient process of merging into a single, larger structure. 2.5 million light-years is a distance so vast that the light currently reaching your eyes, if you were somehow able to see Andromeda directly and clearly tonight, left that galaxy 2.5 million years ago. Long before modern humans existed in anything resembling our current form, back when our early hominid ancestors were still, patiently, slowly, evolving across the plains of what is now Africa. And even this enormous span, 2.5 million light-years encompassing our entire nearby galactic neighborhood, remains, in the context of tonight's full journey, still relatively local. Still, in the grand scheme of everything we're building toward, comparatively close to home. Beyond the Local Group lies something considerably larger still, the Virgo supercluster, an enormous, loosely bound collection of galaxy groups and clusters spanning roughly 110 million light-years across, containing perhaps 100,000 individual galaxies, including our own Local Group as one small component within its much larger structure. And beyond even the Virgo supercluster lies something larger still, a genuinely vast structure that astronomers have only properly mapped and named within the past decade or so, called Laniakea, a Hawaiian word meaning immeasurable heaven, chosen specifically because it captures both the structure's genuine scale and the almost spiritual sense of awe it inspires in those who study it. Laniakea is a supercluster of superclusters, an enormous, gravitationally interconnected web of galaxy clusters spanning approximately 500 million light-years across, containing roughly 100,000 large galaxies, all of them, including our own Milky Way, slowly, patiently flowing along shared gravitational currents toward a distant, still not fully understood region of unusually strong gravitational attraction that astronomers have given the evocative, slightly unsettling name of the Great Attractor. 500 million light-years. at this scale, individual galaxies. Those vast collections of hundreds of billions of stars that seemed, just a few steps ago in tonight's journey, like the largest structures imaginable, become, themselves, merely individual points of light within an even larger, even more intricate cosmic architecture. The universe, at this scale, begins to resemble something closer to a vast, three-dimensional web or sponge. Dense filaments and clusters of galaxies stretched across enormous cosmic voids, the whole structure looking, when properly mapped by patient astronomers over decades of careful observation, remarkably similar to the branching, interconnected structure of neurons in a human brain, or the delicate threads of a spider's web caught in morning light. Wherever you are, I hope you're comfortable. We're approaching, now, the point in tonight's journey where the numbers stop growing merely large and begin growing genuinely, properly cosmic. Let's take a slow breath together before we take that final, enormous step. Everything we've discussed so far tonight, from your own bedroom, out through the solar system, out through our galaxy, out through the local group, the Virgo supercluster, and finally Laniakea itself, spanning some 500 million light years. All of it, taken together, still represents only a comparatively small fraction of what astronomers actually mean when they talk about the size of the universe. Because now we need to talk about the observable universe itself, the true, full boundary of everything it is physically possible for any instrument, any telescope, any observation ever made by human beings to actually detect. And to understand this boundary properly, we need to return to that idea I asked you to carry with us from the very beginning of tonight's journey. The simple, strange fact that looking outward into space always means looking backward into time. Let me walk you through this carefully, because it's the single most important idea in tonight's entire conversation, and because understanding it properly is what finally allows the true, staggering size of the observable universe to make sense. The universe, according to the careful, patient, decades-long work of modern cosmology, began approximately 13.8 billion years ago in the extraordinary event we call the Big Bang. Not an explosion happening at some single point within a larger, pre-existing empty space, but the origin of space and time themselves, an almost unimaginably rapid expansion from an initial state of enormous density and heat occurring everywhere at once, with no center and no edge in any conventional sense. Since that moment, light has been traveling outward from every point in the universe, in every direction, at its fixed, unchanging speed. And because the universe is 13.8 billion years old, the most distant light that could, in principle, have had time to reach us by now is light that has been traveling for the entire span of the universe's existence. 13.8 billion years. This might lead you to a very reasonable, very intuitive first guess that the observable universe, the full sphere of everything we could possibly have seen by now, should have a radius of 13.8 billion light years, and therefore a total diameter of about 27.6 billion light years. And this guess, reasonable as it seems, turns out to be wrong. Not because the math is flawed, but because of something we've touched on throughout this entire series here at Late Space, something genuinely strange and genuinely wonderful about the nature of space itself. The universe has been expanding continuously this entire time, and that expansion changes everything about how we need to calculate this final distance. Let me explain this carefully, patiently, because it's genuinely one of the more mind-bending ideas in all of cosmology, and it deserves to be properly understood rather than simply stated. Imagine a particular beam of light emitted from some distant galaxy very early in the universe's history. Let's say only a few 100 million years after the Big Bang, when the universe was still very young. That light begins its long journey toward us, traveling at its fixed, unchanging speed, crossing the space between that ancient galaxy and our own eventual location. But here is the crucial, genuinely strange part. The space itself, through which that light is traveling is not staying still. It's expanding continuously throughout the entire 13.8 billion years that light has been in transit. The very fabric of space between that ancient galaxy and us has been stretching, growing, expanding, carrying that distant galaxy and countless others like it further and further away from where they originally were, even as the light they emitted continues, faithfully, at its own fixed pace, toward us. By the time that ancient light finally reaches our telescopes today, light that started its journey when the universe was only a few 100 million years old, the actual galaxy that originally emitted it is no longer at the distance it was when the light departed. Because of billions of years of continuous cosmic expansion, that galaxy is now, right now, at this very moment, considerably farther away than it was when its light first began the journey toward us. Cosmologists have a specific term for this actual, present moment distance, accounting for all of the intervening cosmic expansion. They call it the comoving distance. And when you properly calculate the comoving distance to the very edge of what we can observe, to the most ancient, most distant light that has had time to reach us since the Big Bang, the answer is not 13.8 billion light years. It is approximately 46.5 billion light years. The observable universe, therefore, measured as a sphere with Earth at its center, extending outward 46.5 billion light years in every single direction, has a total diameter of approximately 93 billion light years. Wherever you are, I hope you're still comfortable. I want to sit with that number for a while, because I think it deserves considerably more than a passing mention before we move any further. 93 billion light years. Let's try, one more time, to feel this properly, the way we've tried to feel every measurement tonight, building carefully from something small and comprehensible towards something almost beyond comprehension. Our entire solar system, from the Sun out through the distant, sparse edges of the Oort cloud, spans roughly 2 light years. The distance to our nearest stellar neighbor, Alpha Centauri, is 4.2 light years. Our entire galaxy, containing hundreds of billions of stars, spans roughly 100,000 light years. The distance to our nearest large galactic neighbor, Andromeda, is 2.5 million light years. Laniakea, the vast supercluster structure containing our entire galaxy and roughly 100,000 others, spans approximately 500 million light years. And the full diameter of the observable universe, the true, complete boundary of everything any instrument has ever had the physical possibility of detecting, is 93 billion light years, nearly 200 times larger than Laniakea itself, a structure so vast that our entire galaxy, containing our entire solar system, containing this entire planet, containing every single person who has ever lived, becomes, at this final scale, not even a visible point. Simply one infinitesimally small piece of matter, among an almost uncountable number of similarly small pieces, scattered across a sphere of space so large that the mind, quite honestly, simply cannot hold it. I want to spend some time now on something that I think is genuinely important, genuinely worth sitting with carefully, because it's easy, having just arrived at this staggering 93 billion light-year figure, to assume that we've now reached the actual, final, true edge of everything that exists. We have not. The observable universe, vast as it undeniably is not the same thing as the universe. It represents, specifically and precisely, only the portion of everything that exists that we, from our particular vantage point on this particular small planet, have had the physical opportunity to observe, given that light travels at a fixed speed, and the universe has only existed for 13.8 billion years. Beyond that 46.5 billion light-year horizon, in every direction surrounding our entire observable sphere, the universe, as far as current physics can determine, almost certainly continues. Not because we've detected anything out there directly, which by definition we cannot have, since any light from beyond that horizon simply hasn't had time to reach us yet. But because there is no known physical reason, no theoretical mechanism, that would cause the universe to conveniently stop existing precisely at the boundary of what we happen to be able to see from our own particular location. This is worth genuinely sitting with, because it reveals something quietly humbling about the entire scale we've just spent this whole conversation carefully building. Everything we've discussed tonight, every step outward, from your bedroom to the moon to the sun to the edges of our solar system to our galaxy to Laniakea to the full 93 billion light-year diameter of the observable universe itself. All of it represents only what we, specifically, from this one particular vantage point, are capable of seeing. It is not the size of everything. It is, more precisely, the size of everything visible to us. How much larger might the true, total universe actually be? Here, I want to be as honest and as careful as I can, because this is genuinely one of the more open, more actively debated questions in modern cosmology, and I don't want to leave you with false certainty where genuine uncertainty is the more honest answer. Some cosmological models, extending from what's called inflation theory, the idea that the very early universe underwent an extraordinarily brief but extraordinarily rapid period of expansion, far faster even than the ordinary cosmic expansion we've discussed throughout tonight, suggest that the true, total universe could be dramatically larger than what we can observe. Some estimates place this figure at roughly 250 times larger than the observable universe, corresponding to a total diameter of something in the range of 3.4 trillion light-years. Other, more speculative models drawing on the mathematics of eternal inflation suggest figures that grow so large, so quickly, that they become genuinely difficult to even properly express in ordinary numerical notation. Figures involving towers of exponents stacked upon exponents, numbers so vast that writing them out in full would require more digits than there are atoms in our entire observable universe. And some models, taking seriously the observation that space, on the largest scales we can measure, appears remarkably flat, meaning that parallel lines, extended far enough, would remain parallel rather than curving back toward each other or diverging apart, suggest that the universe might genuinely, truly be infinite. Not unimaginably large, but literally, mathematically, without any boundary or edge at all, extending forever in every direction, containing, somewhere within that infinite expanse, an infinite number of galaxies, an infinite number of stars, and, if certain physical processes really do repeat themselves given infinite space and infinite time, quite possibly an infinite number of near-exact repetitions of everything that has ever happened, anywhere, including, somewhere, impossibly far away, an exact repetition of this very moment, this very room, this very conversation. I want to be honest that this last possibility, while genuinely permitted by some interpretations of the mathematics, remains deeply speculative, and many cosmologists would rightly caution against treating it as anything more than an interesting theoretical curiosity rather than an established scientific finding. But even setting aside the most extreme speculative possibilities, the more conservative, more widely accepted position among cosmologists today is this: the total universe is almost certainly considerably larger than what we can observe, quite possibly by an enormous margin, and quite possibly genuinely infinite. Wherever you are, I hope you're comfortable. Let's sit with the weight of that for a moment, because I think it deserves real, unhurried attention, rather than being rushed past towards some tidy, comfortable conclusion. We have spent this entire conversation together, carefully, patiently, building outward from your own bedroom to a sphere 93 billion light-years across, containing, within it, some 2 trillion galaxies, each one containing, on average, hundreds of billions of individual stars. And having arrived, finally, at that almost unimaginable figure, we now find ourselves having to acknowledge, honestly, that even this staggering, almost impossible to hold sphere of space and time, represents, quite possibly, only the smallest, most local fraction of everything that actually exists. There is a particular kind of vertigo in this realization, I think, if you let yourself fully feel it. Not a frightening vertigo, exactly, though I understand if it initially registers that way. More like the specific, disorienting feeling of looking down from somewhere very high and realizing that the ground you thought you could see clearly actually extends much further than your eyes could initially process. That what looked, at first glance, like the entire visible landscape was, in fact, only the nearest, most immediately apparent portion of something considerably larger, stretching away toward horizons your eyes were simply never capable of resolving. I want to offer you something now, gently, at this hour, because I think it's important, having spent this much time with numbers this large, to come back to something more immediate, more human, more genuinely comforting. There is a particular way of holding vastness like this that I think serves us better than either denial or despair, better than pretending these numbers don't really matter to how we live our lives, and better than being genuinely overwhelmed or frightened by them. It's the way, I think, that the very astronomers and cosmologists who spend their entire careers carefully measuring and mapping these staggering distances actually seem to hold them, based on how they talk about their work, based on the evident wonder and genuine joy so many of them express, even after decades spent professionally confronting numbers this large. The size of the universe, staggering as it is, does not diminish the significance of what happens on this one particular small planet, in this one particular small room, in this one particular quiet moment tonight. If anything, I think it does something closer to the opposite. It reveals, by sheer contrast, exactly how remarkable it is that anything capable of understanding scale like this, any arrangement of matter capable of building telescopes, of doing the patient mathematics of cosmic expansion, of sitting quietly in a dark room at night and genuinely, sincerely wondering about the size of everything, has ever managed to exist at all. You are, right now, a small, specific, genuinely remarkable arrangement of atoms, resting on a small, specific, genuinely remarkable planet within a small, specific, genuinely remarkable galaxy, somewhere within a sphere of space and time so large that even our most careful, most patient calculations struggle to properly express it. And within that almost incomprehensible vastness, you have spent this evening doing something genuinely extraordinary, taking the time, deliberately, patiently, to actually try to understand, properly, honestly, just how large the space around you actually is. That is not a small thing. In a universe this vast, the fact that any part of it has organized itself into something capable of turning around and measuring the whole, capable of building the telescopes, developing the mathematics, and patiently, carefully working out the actual, real distance from a single bedroom to the edge of everything observable, is genuinely one of the more remarkable things the universe has ever produced. Let me tell you something about the specific human effort behind these numbers, because I think it's worth honoring properly here at the end of tonight's long journey outward. Every single figure we've discussed tonight, the precise diameter of Earth, the exact distance to the Moon, the careful measurement of the astronomical unit, the definition and calibration of the light year, the patient mapping of our galaxy's structure, the discovery and naming of superclusters like Laniakea, and finally, the careful, decades-long calculation of the observable universe's true, expansion-adjusted diameter. Every one of these figures represents the accumulated, patient work of countless individual scientists working across centuries, each one building carefully on the work of those who came before them. The cosmic distance ladder we touched on earlier in tonight's journey, that careful, step-by-step method of measuring progressively larger distances, each rung calibrated against the one below it, required the individual contributions of astronomers across more than a century of careful, patient observation. Henrietta Swan Leavitt, working through countless photographic plates in the early 1900s, painstakingly cataloguing the brightness of pulsating stars, discovered the relationship between a star's pulsation period and its true luminosity that would eventually allow astronomers to measure distances to other galaxies entirely. Edwin Hubble, building directly on her discovery, used it to first establish that the fuzzy nebulae astronomers had been observing for centuries were, in fact, entire separate galaxies, and that those galaxies were, remarkably, moving away from us. The first direct evidence of the cosmic expansion that has been central to everything we've discussed tonight. Generations of astronomers since have refined, extended, and cross-checked these original measurements using increasingly sophisticated instruments. Ground-based telescopes, then space telescopes like Hubble, and now, in our own current moment, the extraordinary infrared vision of the James Webb Space Telescope. Each new generation of instruments allowing for more precise, more confident calculations of exactly how large and exactly how old the observable universe actually is. The number we arrived at tonight, 93 billion light-years, is not a figure that arrived easily or quickly or without enormous patient effort. It represents, quite genuinely, one of the great collaborative achievements of human civilization, the careful, generational, painstaking measurement of the largest thing it is possible for any observer to measure. Wherever you are, I hope you're still comfortable. We're nearing the end of tonight's long journey outward, and I want to spend these final minutes bringing us gently, carefully, back home, back to exactly where we began. Because here is something worth holding, I think, as we prepare to close tonight's conversation. The entire journey we've taken together this evening, from your bedroom, out through the solar system, out through our galaxy, out through Laniakea, out to the full 93 billion light-year diameter of everything observable. That entire journey, however vast it felt while we were making it, is also, in a very real and immediate sense, a journey you have taken without moving at all. You are still exactly where you started, still in the same room, still wrapped in the same blanket, resting on the same surface, breathing the same slow, unhurried breath you were breathing when we began. The entire staggering scale of the observable universe, every star, every galaxy, every supercluster, every distant ancient point of light that has been traveling toward us since the very earliest moments after the Big Bang. All of it, in some sense, exists simultaneously with and around this one small, quiet, specific place where you happen to be resting tonight. This is, I think, one of the more genuinely comforting things about properly understanding cosmic scale, rather than simply being overwhelmed by it. The vastness doesn't require you to go anywhere. It doesn't require you to somehow shrink yourself down to match its own significance, or expand yourself outward to somehow properly encompass it. It simply exists, all around you, at every scale simultaneously. From the smallest, most intimate scale of this particular room to the largest, most incomprehensible scale of the observable universe itself. And you, right now, tonight, are simply, quietly, present within all of it, exactly as you are. Let's come down now, slowly, gently, toward the end of tonight's long conversation. Here is what is true, as carefully and as honestly as I can leave it with you. From where you're resting right now, the moon sits about 384,000 kilometers away, its light reaching you after roughly a second and a quarter. The sun sits about 150 million kilometers away, its light reaching you after roughly 8 minutes. Our solar system, out to the edges of the Oort cloud, spans roughly 2 light-years. Our nearest stellar neighbor, Alpha Centauri, sits 4.2 light-years away. Our entire galaxy, containing hundreds of billions of stars, spans roughly 100,000 light-years. Our nearest large galactic neighbor, Andromeda, sits 2.5 million light-years away. The vast supercluster structure containing our galaxy, called Laniakea, spans approximately 500 million light-years, and the full diameter of the observable universe, the true, complete boundary of everything any instrument has ever had the physical possibility of detecting, properly accounting for nearly 14 billion years of continuous cosmic expansion, is approximately 93 billion light-years. Beyond that boundary, the universe almost certainly continues, quite possibly for an enormous additional distance, quite possibly, genuinely, forever. And within all of that, within this almost incomprehensible nesting of scales, each one dwarfing the one before it, stretching outward from your own quiet room to the very edge of everything observable and, likely, considerably further still, you are here. Specifically, particularly, genuinely here. Not lost within the vastness, simply present within it, the way every single point in an infinite universe is, in its own way, equally present, equally real, equally part of the whole staggering structure we've spent tonight carefully, patiently trying to properly measure. I want to leave you with one final image before we close, because I think it captures, better than any additional numbers could, the particular feeling I hope you carry with you into sleep tonight. Picture, if you can, a very old photograph. One taken by the Voyager 1 spacecraft in 1990, from a distance of about 3.7 billion miles, as it looked back one final time toward the solar system it was leaving behind forever. In that photograph, Earth appears as a single, tiny, pale blue point of light, less than a pixel across, nearly lost within a scattered ray of sunlight crossing the camera's lens. That photograph was taken from a distance of only 3.7 billion miles, a distance that, measured in light years, amounts to something less than 1/10,000th of a single light year. And even from that comparatively modest distance, Earth had already become almost invisible, a barely perceptible speck within an already vast, dark, largely empty field of view. Now imagine extending that same perspective outward, not by a mere 3.7 billion miles, but by 93 billion light years. A distance so much larger that the entire comparison essentially breaks down, becomes almost meaningless. The numbers simply too different in scale to sensibly relate to one another at all. And yet, somewhere within that entire, almost incomprehensible sphere, in one small, specific, unremarkable corner of one small, specific, unremarkable galaxy, you are here, lying still, breathing slowly, having spent this entire evening, patiently, carefully, doing something genuinely remarkable, trying to properly understand, honestly and clearly, the true scale of the space surrounding you. That is not nothing. In a universe this large, the fact that any small part of it has learned to measure the whole, has built the telescopes, developed the mathematics, and patiently, generation after generation, worked out the actual distance from one quiet bedroom to the very edge of everything observable, is, I think, genuinely one of the most remarkable things the universe has ever managed to produce. Close your eyes, if they're not already closed. Right now, this very moment, somewhere 93 billion light years away in every single direction, the observable universe reaches its faint, expansion-stretched edge. The oldest light there is, still arriving, still being patiently gathered by telescopes here on Earth, carrying with it information about a universe still in its earliest, most unformed infancy. And here, in this one small room, on this one small planet, orbiting this one small star, within this one small galaxy, you are resting, quietly, specifically, genuinely present within the whole vast, nested structure of everything we've discussed tonight. Thank you for spending this time here. Thank you for taking this long, patient journey outward, step by careful step, and for letting the universe be exactly as large, exactly as strange, and exactly as genuinely wondrous as it actually is. Sleep well, And somewhere in every direction around you, at every scale, from the width of this room to the edge of everything observable, the universe continues, quietly, patiently, exactly as it always has. Good night.